To the lesson 33 activities. We're going to use another log scale to talk about pH, measuring the acidity of a liquid. So we have a formula that measures a liquid's acidity. pH values are usually between 0 and 14. 7 is considered neutral, and that was the pH of water. A substance with a pH less than 7 is acidic, greater than 7 is basic, and this is the formula. pH is the negative log of the concentration of hydrogen ions, which is measured in moles per liter. So we want to find the pH of shampoo, knowing that the concentration of hydrogen ions is 7.4 times 10 to the negative 10 moles per liter. Determine if it's acidic or basic. We'll round our answer to the first decimal place. So pH is the negative log of the concentration of hydrogen ions, which is 7.4 times 10 to the negative 10. And we'll just pop that into a calculator. Negative log of 7.4 times 10 to the negative 10. Close the parentheses, and we get 9.1 if we round to the nearest decimal. So that would be basic. Greater than 7, it's a base. Okay, now going in reverse, I've given you the pH of this certain kind of beer, which means it's acidic because 4.1 is less than 7. So we have an acid, and I want to find out what is the concentration of hydrogen ions. So I'm just going to write my formula. pH is the negative log of the concentration of hydrogen ions. And I know the pH is 4.1. That's negative log of the concentration of hydrogen ions, which is what I'm looking for. So I want to get the log by itself. So I'm going to multiply both sides of this equation by -1. So I have negative 4.1 is equal to the log of the concentration of hydrogen ions. And then I'm going to switch it to an exponential equation because there's an itty bitty invisible 10 there. Switch to an exponential equation, that's my base. The log always equals the exponent, and that equals the concentration of H+. So I just have to, in my calculator, type 10 to the negative 4.1 so that I can write it in scientific notation, which is 7.9 times 10 to the negative 5, which that just means move your decimal point 5 places to the left, so I have 0.000079. Either of these would be acceptable. Okay, here's another log scale. It's the decibel scale. It's designed to reflect human perception of sound. So just like pH and the Richter scale, it's logarithmic. Noise levels are measured in units called decibels. And average conversation is at about 50 decibels. I naught is the reference sound, the faintest sound we're able to hear. It's 10 to the negative 12 watts per meter squared. And we let I represent the intensity of the sound. Then the noise level N, which is measured in decibels, is 10 times the log of I over I naught. All right, so if I over I naught is 100, we want to calculate the noise level in decibels. So just writing out the formula, it's 10 times the log of I over I naught. So if I over I naught is 100, I'm just going to put 10 times the log of 100. And the log of 100 is 10 to what power is 100? That's 2. So this is 10 times 2, which is 20 decibels. What if we increase I over I naught to 1,000? So this is N equals 10 times the log of 1,000. So that's 10 times Log of 1,000 is 3 because 10 to the third power is 3. So that's 30 decibels. What is the decibel of a typical rock band if its intensity is 10 to the negative 1 watts per meter squared? So here's my formula. N is 10 times the log of I over I naught. And I'm going to put in the stuff that I know. So 10 times the log. The intensity of my sound is 10 to the negative 1. The intensity of my reference sound, I naught, they told me earlier here, was 10 to the negative 12. So this is 10 times the log. I'm going to simplify this expression here. Remember, when you're dividing exponents, you would subtract, dividing like bases, you subtract the exponents. So this becomes, the base is still 10, then you would do negative 1 minus negative 12, which is actually plus 12. So this becomes 10 to the 11. So the log of 10 to the 11 is 11. So we get 110 decibels would be the noise level at a rock concert. Now, I know the decibel level of typical conversation. I want to know its intensity. So I have to plug everything in, write down my formula, and I'm going to be solving for I. I put everything else in. So I've got N is 50. 10 times the log of I don't know. I naught is 10 to the negative 12. And I want to solve for I. So I'm going to start by dividing both sides by 10. So I have 5 equals the log of I over 10 to the negative 12. Switch to exponential form. So this says 10 to the 5th equals I over 10 to the negative 12. And then multiply both sides by 10 to the negative 12. So my intensity is 10 to the negative 7 because I added the exponents. Multiplying like bases, add the exponents. How many orders of magnitude, that is powers of 10, more intense is the sound of a rock band than average conversation? So the intensity for a rock band is 10 to the negative 1 compared to average conversation, which is 10 to the negative 7. So how many powers of 10 larger is 10 to the negative 1? 6 powers of 10. Negative 7 to negative 1 is a difference of 6. All right, here I've given you a scatter plot, and we want to talk about whether we should use a linear function, a log function, or a logistic function to model the data. So I see a pretty standard S-shaped curve. You've got this increasing quickly part and followed by increasing less quickly. So I'm thinking logistic. I used some computer software to come up with regression models using 3 different types of functions: linear, logarithmic, and logistic. And I just want to plug 35 into each of them. So I'm just going to use my calculator to type these all in. So h of 35, my linear function, so I've got 26.07, replacing my x with a 35, plus 223.67 is 1,136.12. All right, I'm going to do something similar for my log model. So I have negative 812.13 plus 602.87 ln of 35. 1331.28. And finally, my logistic function 1707.116 divided by, parentheses around the whole denominator, 1 plus 12.2327 e to the negative 0.1207 times 35. And then close the parenthesis that was around the denominator, and I get 1447.93. Okay, we've got one more log scale to study. You can see we use log scales to measure a lot of real life phenomenon: earthquakes, sound, pH, and now the brightness of a star. So astronomers use the word magnitude, just like we do with an earthquake. If the star has a brightness of B, its magnitude is defined as negative 2.5 times the log of B over B naught. B naught is a constant, the reference brightness. Originally, the brightness of Vega was used as the reference brightness, but it's a little different now, and it doesn't really matter. We're just going to know that it's some constant. If a star is 10 times as bright as its reference brightness, that is, B is 10 times B naught, what is its magnitude? So M is going to be negative 2.5 times the log. B over B naught would be 10. So the log of 10 is 1. So this is negative 2.5 times 1, which is negative 2.5. If a star is 1/100th as bright as its reference brightness, calculate its magnitude. It's negative 2.5 times the log of 0.01, 1/100th. So the log of 0.01 is negative 2. So this is negative 2.5 times negative 2, which is 5. If a star is half as bright as its reference brightness, M is going to be negative 2.5 times the log of a half. That I'm going to need a calculator for, because a half isn't an obvious power of 10. Negative 2.5 times the log of 0.5, and I get 0.75. The sun is roughly 4.92 times 10 to the 10th times as bright as the reference brightness. What is its magnitude? So I put 4.92 times 10 to the 10th in here. Negative 26.7. All right, I want to use the laws of logarithms to expand the right-hand side of the equation. So M is negative 2.5 times the log of B over B naught. So that's a division, so I can expand that into a subtraction. So I have negative 2.5 times the log of B minus the log of B naught. So what happens to the magnitude as stars become brighter? So if B is brighter than B naught, then that subtraction is going to be positive, and then you're going to multiply it by a negative number. So it's, as stars become brighter, your magnitude gets smaller, right? Or I should say more negative. Or maybe maybe decreases is a better way to describe it. As the brightness goes up, the magnitude actually goes down. So you might notice that the sun had a very negative magnitude, even though it's very, very bright, right? It's clearly our brightest star, yet it has a magnitude of negative 26.7. So that is weird, right? It feels weird, and it apparently comes from an ancient Greek classification system where the brightest stars were of the first magnitude and the dimmest were of the sixth magnitude. So the brightest ones had a smaller number. So in more modern times, we've kind of stuck with a similar system.